The drill bit has just broken through 56 million years of rock. What it brings back should not look familiar, but it does. Inside that core sample, the chemistry does not match any known natural event. It matches something else entirely, something that should not have existed yet. The scientists watching it emerge are not confused. They are unsettled. Not because the data was wrong, because it was right, and if it is right, it's a trace of activity from a time before us. Our place in Earth's history is no longer certain. We have always assumed we were the first species on this planet to build cities, to split atoms, to reroute rivers and wrap the atmosphere in an invisible chemical shroud of our own making. That assumption has never seriously been challenged, not because the evidence for it is overwhelming, but because almost no one has ever thought to look hard enough to test it. In 2018, 2 scientists did. What they found, or more precisely, what they realized they could not rule out, will change the way you think about this planet, about deep time, and about what it truly means to leave a mark on a world that has been erasing marks for 4.5 billion years. This is the story of the Silurian hypothesis. The question of whether Earth has already watched civilizations rise and fall, and whether the rock beneath your feet carries buried evidence of something that came before. Welcome to Still Science, where questions follow the evidence. Start with the number. 4.5 billion years. That is how old this planet is. Write it out in full. 4,500 million years. It is a number that resists comprehension. The human brain is not built to hold it. Our intuitions about time are calibrated to human lifetimes, to centuries of recorded history, to the 10,000-year arc from the first permanent settlements to the present day. Against the age of this planet, those 10,000 years represent roughly 0.0002% of total elapsed time. A fraction so small, it does not register on any ordinary scale. Compress the entire history of Earth into a single calendar year, where January 1st is the formation of the planet, and December 31st at midnight is today. On that calendar, the first single-celled organisms appear sometime in mid-March. The first complex multicellular life does not show up until mid-November. Dinosaurs arrive in mid-December and are gone by December 26th. The entirety of human prehistory, every cave painting, every stone tool, every campfire lit by Homo sapiens since the species first emerged, occupies the last 22 seconds of December 31st. Industrial civilization, the era of burning fossil fuels, of steel and concrete and nuclear power, is the last fraction of the last second. A blink. Less than a blink. The question that the Silurian hypothesis poses is deceptively simple. In the remaining time on that calendar, all of November, all of December before the last few seconds, was there ever another blink? Was there, somewhere in the vast and largely unexamined archive of Earth's past, another species that crossed the threshold from biology into technology? A species that built, burned, extracted, and altered? A civilization that rose and fell so far back in geological time that the planet has had millions of years to dissolve every trace of its existence? Before you dismiss this as science fiction, consider what dismissal actually requires. To say with confidence that no such civilization ever existed, you must first be confident that the geological record would preserve evidence of it, that scientists would recognize such evidence if they found it, and that the absence of obvious artifacts constitutes meaningful proof of absence. The 2 scientists who formalized this question, astrophysicist Adam Frank of the University of Rochester and climate scientist Gavin Schmidt of NASA's Goddard Institute for Space Studies, examined all three assumptions carefully, and they found that every single one of them is weaker than we have been assuming. Their 2018 paper in the International Journal of Astrobiology did not claim that a previous civilization existed. They were explicit about doubting it. But what their analysis demonstrated was something that science rarely admits and almost never broadcasts. We do not actually know. The geological record cannot rule it out. The methods we use to study the deep past were not designed to detect the signatures of technology, and the absence of obvious ruins tells us far less than we think. That is the discomfort at the heart of this story. Not a confident claim about what happened. A precise and rigorously established uncertainty about what we can know. That uncertainty, properly understood, opens a door that most people assume was permanently shut. To understand why the Silurian hypothesis carries weight, you first need to understand what the geological record actually is and what it is not. Most people picture it as a vast, layered archive, a library of stone in which every chapter of Earth's history is neatly preserved, waiting to be read. This picture is wrong in almost every important detail. The geological record is not a library. It is a ruin of a library, after a fire, after a flood, after centuries of looters. Most of what was ever written has been destroyed. What survives is fragmentary, unevenly distributed, and subject to constant reinterpretation. The processes that created the geological record are the same processes that continuously destroy it. Begin with the ocean floor. The oceans cover 71% of Earth's surface. They seem like the obvious place to look for preserved records of the past. And in some ways they are. Sediment accumulates on the seafloor relatively undisturbed, building up layer by layer, in a way that can preserve chemistry and microscopic fossils across millions of years. But the ocean floor is not permanent. It is created at mid-ocean ridges, where magma wells up from below and hardens into new crust, and it is destroyed at subduction zones, where old, dense oceanic crust dives back down beneath the continents and melts into the mantle. The conveyor runs continuously. The oldest oceanic crust on Earth today is roughly 200 million years old, found in a small patch beneath the western Pacific. Everything older has already been subducted, melted, and recycled. Any evidence of anything that happened on the ocean floor before 200 million years ago, any city on an ancient continental shelf, any chemical signature of industry deposited in ancient seabed sediment has been returned to the planet's interior and destroyed. It is not buried. It is gone. Not lost. Annihilated. Continental crust is more durable. It is less dense than oceanic rock and tends to stay near the surface rather than subducting, which is why some continental rocks are nearly 4 billion years old. But durability is not the same as preservation. The continents have been rearranged by plate tectonics, have collided and split and collided again. Mountain ranges have risen and been worn flat by erosion. River systems have carried material from high ground to sea basins, where it has been buried and compressed and eventually turned into new rock. A chunk of granite that was once part of an ancient highland has probably been chemically altered, physically transported, and structurally reprocessed multiple times in the intervening hundreds of millions of years. Metamorphism takes this further. When rock is buried to sufficient depth, when temperature and pressure reach critical thresholds, the minerals within it recrystallize. Sedimentary layers that once held fossils and chemical records become schists and gneisses, their original structure erased and replaced by something new. The deep past is not simply distant, it is transformed. Now add erosion. At the surface, the forces of wind, water, ice, and temperature work constantly to disaggregate, dissolve, and transport rock material. In humid climates, exposed rock can be worn down by several meters per million years. That rate sounds slow, but over tens of millions of years it means that virtually no original surface material survives. An ancient landscape is progressively planned away. What was once the top layer becomes sediment, transported downstream, deposited elsewhere, buried, and lithified into new rock that no longer resembles what it came from. The net result is that exposed, accessible, unmetamorphosed surface material from more than 10 million years ago is relatively rare. Material from 50 million years ago that has not been disturbed by any of the above processes is a significant find. Material from 100 million years ago in anything like original condition is exceptional. Go back further, and the geological record becomes increasingly sparse, increasingly altered, and increasingly difficult to interpret. This is the reality against which the Silurian hypothesis must be evaluated. Any civilization that existed tens of millions of years ago existed in a world where the surface has since been entirely reworked. Their cities, if they built cities, are gone. Their roads, their mines, their ports, erased. Even their garbage heaps, even the altered landscapes surrounding their settlements, have been pulverized by processes that do not care what they are destroying. The planet is not indifferent to the past. It is actively hostile to it. What, then, could survive? This is the question Frank and Schmidt worked through with genuine scientific rigor, and their answer is worth following carefully. Physical artifacts are the first thing to go. A stone building will survive erosion for tens of thousands of years, perhaps longer in the right conditions, but in geological time, it is not durable. Given 50 million years, there is no material that humans currently use in construction that would remain recognizable. Steel corrodes. Concrete dissolves in acidic groundwater. Glass devitrifies and recrystallizes into unrecognizable mineral forms. Even granite, the most durable common building material on Earth, can be completely destroyed by the slow chemistry of weathering given sufficient time. The pyramids, in 50 million years, will not exist. Not as ruins, as atoms dispersed across the sedimentary record. What might survive are chemical signatures. And this is where the Silurian hypothesis becomes genuinely compelling. Every industrial civilization must, by definition, alter the chemistry of its environment. It burns fuels, producing carbon dioxide and other gases that change the atmospheric composition and leave isotopic traces in sediment. It mines and smelts metals, producing concentrations of heavy elements in places where they would not naturally occur. It generates waste products, complex organic molecules, radioactive isotopes, synthetic compounds that get deposited in soils and sediments and can, under the right conditions, remain chemically detectable for millions of years. We know this not in theory, but in practice, because we are doing it right now. The current geological epoch has been formally proposed for renaming to the Anthropocene, the age of humans, precisely because the chemical signatures of human industrial activity are so clear and so globally distributed that future geologists will be able to identify the precise moment in the stratigraphic record where our civilization became visible. The spike in carbon-13 depleted atmospheric carbon. The global distribution of novel synthetic compounds that have no natural origin. The radioactive signature of nuclear weapons testing, present in every ice core, every sediment layer, every biological sample from every corner of the planet since 1945. The sudden collapse of biodiversity visible in any sediment core across any boundary where the modern era meets everything that came before. All of this will be preserved in the geological record. Future scientists, or any other intelligent species that might someday look back through these layers, will be able to read our presence clearly. Not through artifacts, through chemistry. The critical question is, how long does that chemical signature persist? And the answer depends enormously on which signature you are talking about. The radioactive isotopes from nuclear weapons testing are the least durable. Plutonium-239, the synthetic isotope most characteristic of nuclear technology, has a half-life of roughly 24,000 years. After 10 half-lives, only about 0.1% of the original material remains. After 1,000,000 years, the signal has effectively vanished. After 50 million years, there is nothing detectably there. A previous civilization that used nuclear technology, even extensively, would leave no radioactive trace that we could find today. Synthetic organic compounds, the plastics, the pesticides, the industrial chemicals, are slightly more durable but face a different problem. Complex organic polymers break down over geological time into simpler compounds. After millions of years of diagenesis, the distinctive molecular structures that identify something as synthetic rather than natural have been altered beyond recognition. The compounds are still there in some form, but they look like natural organic material. The smoking gun has been chemically converted into something that looks like ordinary sediment. Heavy metal concentrations, lead, mercury, cadmium, and the other metals that industrial processes concentrate and scatter, are more persistent. Metal ions can remain bound in sediment geochemistry for tens of millions of years, and can sometimes be detected as anomalous concentration spikes even in deep geological sections. This is actually one of the most promising lines of evidence that a future geologist might detect for our civilization, and one of the few that might persist long enough to remain detectable from truly deep geological time. The most durable signature of all is carbon isotopes. When industrial civilization burns fossil fuels, it releases carbon that has been locked underground for hundreds of millions of years. That ancient carbon has a distinctive isotopic fingerprint. It is depleted in carbon-13, the slightly heavier stable isotope of carbon, because the organisms that became fossil fuels preferentially incorporated the lighter, carbon-12, during their lifetimes. Burning fossil fuels at industrial scale injects enormous quantities of this carbon-13 depleted carbon into the atmosphere, and that shift registers in the sedimentary record as a negative carbon isotope excursion, a sudden drop in the ratio of carbon-13 to carbon-12 that is measurable in marine sediments, in carbonate rocks, in ancient soils. This kind of chemical trace can persist in the geological record for hundreds of millions of years if the sediments that recorded it are preserved. That last clause is the critical one, if the sediments are preserved, which, as already established, is a matter of extraordinary geological luck. Now consider the time frame seriously. Our industrial civilization is approximately 300 years old. The carbon-13 excursion it has produced is real, measurable, and globally distributed. But compressed into the stratigraphic record as a geological layer, that 300 years occupies a thickness of sediment that can be measured in millimeters. In many environments, it is thinner than a sheet of paper. In environments with low sedimentation rates, it may not be resolvable at all. The signal is there, but the time resolution of the record is insufficient to separate it from adjacent decades or centuries. Now imagine a previous civilization that lasted 1,000 years, or 5,000 years. Even at the high end, that civilization's entire industrial impact, if it resembled ours in any meaningful way, would leave a chemical layer no thicker than a few centimeters at most. A layer that, after tens of millions of years of compaction, would be reduced to something thinner still, a layer that would need to have been deposited in an environment with stable sedimentation, avoided subduction, avoided metamorphism, avoided deep burial, survived tectonic disruption, and been exposed at the surface in a location where a geologist happened to be drilling, and then recognized as significant rather than dismissed as a local anomaly. The probability of that chain of circumstances working out is not zero, but it is very, very low. This is not a rhetorical point about the limitations of science. It is a rigorous probabilistic assessment. Frank and Schmidt ran through it carefully and arrived at a conclusion that deserves to be stated plainly. If an industrial civilization had existed on Earth 50 million years ago and had operated at roughly the scale of our own civilization, the geological record as it currently exists probably would not allow us to detect it. Not because the evidence was never there, because the planet has had 50 million years to destroy it. The absence of evidence, in this context, tells us almost nothing. This conclusion requires a particular kind of intellectual honesty to sit with. The scientific temperament tends toward confidence. Scientists prefer to say what they know, rather than what they do not. The Silurian hypothesis demands the opposite, a careful enumeration of what is genuinely unknowable, even in principle, given the tools we have and the state in which Earth's geological record currently exists. But there is a second dimension to this problem that goes beyond simple preservation. It concerns how we interpret the signals we do find. When a geologist finds an anomalous carbon isotope excursion in a sediment core, the first question asked is never, could this be the signature of a previous industrial civilization? The first question, and typically the last question, is what natural process caused this? Volcanism? Methane hydrate destabilization? Changes in oceanic circulation? Orbital forcing? The interpretive framework built into geological science assumes natural causes because in the overwhelming majority of cases, natural causes are the correct explanation, and there is no reason to invoke anything else. But that assumption, however reasonable in practice, creates a systematic blind spot. If an industrial civilization's chemical signature is indistinguishable from certain natural events, and as Frank and Schmidt showed, it largely is, then our interpretive framework will consistently classify it as a natural event, not out of incompetence, out of the entirely rational application of Occam's razor. The simpler explanation is preferred. The problem is that Occam's razor is a heuristic tool, not a guarantee of truth. It works well when the space of possible explanations has been correctly defined. It fails when there is a class of explanations that has been implicitly excluded without examination. Before 2018, the possibility of previous industrial civilizations was effectively outside the space of explanations that geological science considered. It was not that geologists looked at anomalous chemical signatures and consciously rejected the industrial civilization hypothesis. It was that the hypothesis never appeared in the consideration set at all. Frank and Schmidt changed that, not by finding new evidence, but by asking a question that no one had formally asked before. What would an industrial civilization look like in the geological record? And by answering it rigorously enough that the answer can now be held up against existing anomalies and compared. This is how science is supposed to work. A new question reshapes the interpretive framework and forces a re-examination of data that was previously considered understood. The data itself does not change. What changes is the range of explanations available to apply to it. There is one anomaly in the geological record that this new framework demands be examined with particular attention. It is not obscure. It is one of the most studied events in the history of Earth science. But its causes remain, despite decades of intensive research, incompletely understood. And when you look at it through the lens of the Silurian hypothesis, it is unsettling in a very specific way. 56 million years ago, something happened to this planet. The geological record marks it precisely. A boundary layer in sediment cores from every ocean, every continent, every environment where sediment from that era has been preserved. Below the boundary, the chemical signature of one world. Above it, a different world. The transition is geologically rapid, compressed into a window of perhaps 6,000 to 20,000 years, which in geological terms is almost instantaneous. Scientists call this event the Paleocene-Eocene Thermal Maximum, or the PETM. It is the most dramatic climate disruption of the last 66 million years, the most dramatic since the asteroid that ended the dinosaurs, a full 10 million years before the PETM occurred. Here is what the record shows. Over that brief window at the PETM boundary, an enormous quantity of carbon was injected into the atmosphere and oceans. Estimates of the total amount vary with different methodologies, but the most current analyses suggest somewhere between 3,000 and 13,000 petagrams of carbon, a petagram being 1 billion metric tons. For comparison, humanity has emitted approximately 580 petagrams of carbon since the beginning of the Industrial Revolution. The PETM involved at minimum 5 times that quantity, and possibly 20 times, all released in what amounts to a geological eye blink. The consequences were planetary. Global average temperatures rose by 5 to 8 degrees Celsius from an already warm baseline. The Arctic Ocean reached surface temperatures of around 23 degrees Celsius, subtropical warmth at the pole. The deep oceans lost much of their dissolved oxygen, an event called anoxia, which drove the largest deep-sea mass extinction in the past 93 million years. The surface oceans acidified as dissolved carbon dioxide altered seawater chemistry, devastating shell-building organisms. On land, rainfall patterns reorganized completely. In the Bighorn Basin of Wyoming, which has one of the most detailed terrestrial fossil records of this period, the entire mammalian community turned over within the window of the PETM. Old species vanished. New species appeared. The landscape was restructured from top to bottom. Then, over the following 100 to 200,000 years, the planet recovered. Carbon was gradually drawn back down through weathering and biological processes. Temperatures fell. The oceans healed. Life adapted and diversified into the warm world that followed, a world that would eventually cool into the Ice Age cycles of the Quaternary, the epoch that produced our own species. The scar in the rock remains, a thin layer of unusual chemistry, a few centimeters thick in well-preserved sections, sandwiched between ordinary sediment above and below. A whisper that says something extraordinary happened here. What caused it? This is where the science becomes genuinely interesting and genuinely honest. There are 3 major hypotheses for the carbon source at the PETM, and they are not mutually exclusive. The first involves massive volcanism associated with the opening of the North Atlantic. As Greenland rifted away from Europe around this time, enormous volumes of magma intruded into carbon-rich sedimentary rock layers, essentially cooking them and releasing large quantities of carbon dioxide and methane into the atmosphere. This hypothesis is supported by anomalous mercury concentrations in PETM-era sediments from multiple sites. Mercury is a reliable chemical proxy for volcanic activity because volcanoes emit it in large quantities. The second hypothesis involves the destabilization of methane hydrates. These are ice-like molecular structures on the deep sea floor and in permafrost that trap enormous quantities of methane, a greenhouse gas roughly 80 times more potent than carbon dioxide over a 20-year window. When ocean temperatures rise even slightly, hydrates on continental shelves can become unstable, releasing their methane in a cascade. The initial warming triggers more methane release, which drives more warming, which destabilizes more hydrates. A runaway feedback that could account for both the speed and the magnitude of the PETM warming. The third involves orbital forcing. Earth's orbit around the Sun is not fixed. It oscillates through cycles of changing eccentricity, axial tilt, and precession, collectively the Milankovitch cycles, and these oscillations alter how much solar energy reaches different latitudes at different times of year. Some researchers have shown that the onset of the PETM coincided with an orbital configuration that maximized the amount of solar energy received in high northern latitudes, potentially providing the initial thermal kick that triggered the methane feedback. Most current scientific opinion holds that the PETM resulted from a combination of all three mechanisms: volcanic carbon providing the initial pulse, orbital forcing amplifying the warming, and methane hydrate destabilization driving the system into overdrive. This is a plausible explanation. It is a scientifically rigorous explanation. It is almost certainly correct in its broad outlines. But there is a detail that Frank and Schmidt were careful not to overlook, and that no natural explanation has yet fully accounted for. The carbon isotope excursion at the PETM, the sharp negative shift in carbon-13 to carbon-12 ratios that records the sudden injection of large quantities of carbon into the ocean atmosphere system, is more pronounced than the known volcanic mechanism alone can explain. The carbon signature is strongly depleted in carbon-13, which points toward a biogenic source, carbon that originated in living organisms. Fossil fuels are biogenic carbon. Coal, oil, and natural gas are the compressed remains of ancient life, and they carry the same isotopic fingerprint, depleted in carbon-13, that we see at the PETM. This does not mean an industrial civilization caused the PETM. Frank and Schmidt stated unambiguously that they strongly doubt any such civilization existed, and the natural explanations remain far more parsimonious. Methane hydrates also carry a biogenic isotopic signature because the methane they contain was originally produced by microbial activity. The isotopic evidence is consistent with purely natural causes, but here is the point that deserves slow, careful consideration. If an industrial civilization had existed 56 million years ago and had burned through its fossil fuel reserves at anything approaching the scale of modern human industry, the chemical signature it left behind in the geological record would look essentially identical to what we see at the PETM. Rapid carbon-13 depleted carbon injection into the atmosphere, rapid warming, rapid ocean acidification, rapid biodiversity disruption followed by recovery over tens of thousands of years. The two signals are, in many respects, indistinguishable, not because the evidence points toward a previous civilization, but because the evidence cannot tell them apart. We are looking at a scar in the rock, and we know, with certainty, that it records a catastrophe. We know, with high confidence, what the natural mechanisms probably were. But we cannot, with any currently available tool, rule out a contribution from industrial activity. The chemistry does not allow it. The signal is the same either way. Spend a moment with the strangeness of that. We are producing a geological signal right now, burning fossil fuels, releasing carbon-13 depleted carbon into the atmosphere, warming the planet, acidifying the oceans, that will be recorded in the sedimentary layers currently accumulating on ocean floors, in lake beds, in peat deposits around the world. That signal will be compressed by geological processes over the next 50 million years into a thin chemical layer in the rock record. Future scientists, if they exist, examining that layer will see a rapid carbon isotope excursion. They will see evidence of warming. They will see a biodiversity collapse. They will see anomalous concentrations of heavy metals and synthetic compounds that, after 50 million years of diagenesis, will have been altered into something that might look like unusual, but not obviously artificial chemistry. They will apply their interpretive frameworks. They will consider volcanism. They will consider methane hydrates. They will look for a natural explanation that fits the data. Will they think of us? Only if someone in their scientific tradition asks the right question. Only if someone thinks to inquire whether the signal could have been produced by a brief, intense period of technological activity by an intelligent species. Only if the Silurian hypothesis equivalent in their science prompts a re-examination of what the chemistry could mean. This is the recursive quality of the problem that makes it genuinely profound. The very features that make our own industrial activity hard to detect in deep time, its brevity, its chemical overlap with natural events, its dependence on preservation conditions, are the features that make any previous industrial activity equally hard for us to detect. We are reasoning about a detection problem that applies symmetrically to our search for the past and to any future intelligence searching for us. If we cannot guarantee our own detection 50 million years from now, why do we confidently assume that the absence of obvious evidence from 50 million years ago proves no civilization existed? Before moving to the counter-arguments, it is worth dwelling specifically on what the PETM reveals about the detectability problem at its most acute. Because the PETM is not the only ancient carbon anomaly in the geological record, it is simply the most prominent one from the past 66 million years. When the geological record is surveyed across the full span of the Phanerozoic, the last 540 million years, there are multiple events that share the same essential chemical signature: a rapid negative carbon isotope excursion, associated warming, associated ocean acidification, and associated biodiversity disruption. Geologists call these events hyperthermals. The PETM is the largest and most dramatic hyperthermal of the Cenozoic, the last 66 million years, but it is not alone. There are a series of smaller, less extreme events both before and after it, clustered around the Paleocene-Eocene boundary, each showing the same basic chemical pattern at reduced intensity. These events are named Eocene Thermal Maximum 2, the X event, the K/X event, a sequence of lesser hyperthermals stacked in the geological record of the early Eocene, like echoes of the original disruption. Their causes are debated in similar terms to the PETM: volcanism, methane hydrate destabilization, orbital forcing. The natural explanations are plausible for each of them. But here is what that clustering means from the perspective of the Silurian hypothesis. If the PETM itself and the subsequent smaller hyperthermals occurred within a geological window of roughly 3 to 5 million years, centered around 56 million years ago, then this entire cluster of anomalous carbon events occupies a period of geological time with a duration comparable to the typical timescale of a major vertebrate lineage's existence. Something repeatedly destabilized the carbon cycle across multiple million-year intervals in the early Eocene. Each event looks like the others. Each is interpreted using the same natural mechanisms. None has been examined for industrial signatures in any systematic way. Go further back in time to the Mesozoic. The Cretaceous period, which ran from roughly 145 million years ago to the asteroid impact 66 million years ago was the world of the dinosaurs. But it was also a world characterized by unusual warmth, high sea levels, and periodic oceanic anoxic events. These oceanic anoxic events, abbreviated OAS, are intervals during which the deep oceans became severely depleted of oxygen, causing massive die-offs of marine life and leaving distinctive dark, carbon-rich sedimentary layers in the geological record. The most famous of these is OAE2, at roughly 94 million years ago, associated with a significant carbon isotope excursion and widespread extinction of marine organisms. The natural explanation for the Cretaceous OAS involves elevated volcanic outgassing from the large igneous provinces that formed during this period: the Caribbean Plateau, the Ontong-Java Plateau, the Kerguelen Plateau. These were among the most voluminous volcanic events in the last 200 million years, and their carbon dioxide output is estimated to have been substantial, contributing to the generally warm conditions of the Cretaceous. Within this overall volcanic framework, individual OAEs are interpreted as periods of intensified volcanism combined with positive feedbacks from warming-induced release of marine organic carbon. These explanations are well supported and almost certainly correct. The point is not that they are wrong. The point is that the Cretaceous contains multiple episodes of rapid carbon cycle disruption across a 79 million year period, and that within those disruptions, the chemical resolution of the geological record is too coarse to distinguish a brief, intense pulse of industrial origin carbon from the broader volcanic origin carbon background. If something industrial had occurred during the Cretaceous, not once, not as a sustained civilization, but as a brief technological episode lasting thousands of years, it would be invisible in the current chemical record, not because it left no trace, but because its trace is buried in the noise of the larger volcanic signal. Go back further still, to the Permian, and the geological record becomes even more problematic. The end Permian mass extinction 252 million years ago is the most severe in the history of complex life. The Siberian Traps volcanism that drove it released so much carbon dioxide and sulfur dioxide over such an extended period that the chemical signatures of the event dominate the Permian-Triassic boundary sediments globally. Any industrial signal from a hypothetical late Permian civilization, a civilization that might have existed, thrived, and collapsed in the couple of million years before the Siberian Traps made the entire question moot, would be unmeasurably small against the volcanic background, submerged in catastrophe. The farther back in time the hypothetical civilization is placed, the more completely natural events have had time to mask, overprint, or incorporate any industrial chemical signature. This is not a limitation that more sophisticated analytical tools can overcome. It is a fundamental physical constraint. The geological record is not a linear archive, but a palimpsest, and the older the text, the more layers have been written over it. There is a counter-argument that deserves serious attention because it is frequently raised and is not without merit. It concerns fossil fuels. Human industrial civilization was built on coal, oil, and natural gas, energy sources that accumulated over hundreds of millions of years from the compressed remains of ancient life. These resources were waiting for us when we developed the technology to extract and use them. Their presence in accessible surface and near-surface deposits is, in this argument, itself evidence that no previous industrial civilization existed. If a technologically advanced species had discovered these energy sources before us and exploited them at industrial scale, they would be depleted. We would not have found them. The fact that coal seams and oil fields were available for 19th and 20th century industry to discover and exploit suggests that no one had gotten there first. This is a genuine and thoughtful objection. It deserves not to be dismissed, but to be examined carefully. The first limitation of the fossil fuel argument is temporal. The coal measures that powered the first industrial revolution were formed primarily during the Carboniferous period, roughly 300 to 360 million years ago, when vast forests of tree-sized club mosses and ferns accumulated in tropical swamps. The organic material from these forests was buried before the bacteria capable of breaking down lignin, the structural polymer in wood, had fully evolved, which is why the material preserved instead of decomposing. Coal from this period is the geological expression of a specific evolutionary gap that has since closed. A civilization that arose and fell before the Carboniferous period would have had no coal to burn, because the Carboniferous coal deposits did not yet exist. Oil and gas are somewhat different. They have multiple source rocks across multiple geological periods. But the most productive and accessible hydrocarbon deposits are associated with particular geological windows when organic-rich sediments were deposited under the right conditions. So a pre-Carboniferous civilization, one that arose, say, during the Devonian period, 400 million years ago, when complex fish were diversifying and the first forests were appearing on land, would have been working with a completely different energy landscape. The great coal deposits that defined human industry were in the geological future of such a civilization. Whatever energy sources they used, they would not have been depleting the reserves we later found. The second limitation of the fossil fuel argument is technological. We assume that any industrial civilization would follow a path similar to ours: biomass combustion, then coal, then oil and gas, then nuclear and renewables. But this developmental sequence was not inevitable. It was contingent on our specific history, our specific geography, the specific resources available in the regions where industrialization happened to begin. A species that evolved in a different environment, with different available resources, might have developed along a completely different technological pathway. A civilization built on geothermal energy, or on tidal power, or on concentrated solar collection would leave entirely different resource depletion signatures, or none at all on the fossil fuel record. The third limitation is the most subtle. A previous civilization that did burn fossil fuels, but that burned them in a geologically brief window before collapsing, might have depleted certain accessible surface deposits without affecting the deep and dispersed reserves that make up the bulk of the petroleum system. We have been drilling for oil for roughly 160 years. In those 160 years, we have produced on the order of 1 trillion barrels and have identified several trillion more in known reserves. A civilization that operated for 1,000 years, or even 5,000 years, but with less developed extraction technology, might have burned through easily accessible surface seeps and shallow deposits that would be geological noise in the overall petroleum system, without making a measurable dent in the reserves we later discovered through deep drilling. None of these counter-considerations proves that a previous civilization used fossil fuels. They merely establish that the absence of detectable fuel depletion does not prove the absence of a previous civilization. The fossil fuel argument is real evidence with real force, but it is not decisive. There is a second counter-argument: the fossil record of intelligent life. We can trace the evolutionary lineage of modern humans back through the fossil record with considerable precision. Homo sapiens appeared around 300,000 years ago in Africa. Our genus, Homo, extends back roughly 2.5 to 3 million years. Earlier hominins, the Australopithecines, populate the record back to roughly 4 million years ago, and the primate lineage extends much further. The intelligence that underlies human civilization is associated with specific anatomical structures. large relative brain size, particular cortical organization, fine motor control enabling manipulation, that leave signatures in skull shape and hand-bone morphology that are distinguishable in fossils. If a previous species had evolved comparable intelligence and built a technological civilization, shouldn't its fossils tell the story? Shouldn't there be evidence in the fossil record of some creature with the neurological and physical architecture capable of tool use, communication, and coordinated complex behavior? This objection, like the fossil fuel argument, has genuine force, but it also has limits. Fossilization is extraordinarily selective. Paleontologists estimate that the fossils we have found represent, at most, a few % of all species that have ever existed. Many intelligent animals leave very poor fossil records even when their biology is well documented by living observation. Dolphins, octopuses, elephants, all these creatures, with their sophisticated cognition, are underrepresented in the fossil record relative to their actual abundance. An extinct intelligent species that lived in environments where fossilization was rare, coastal zones, tropical forests, island archipelagos, regions later heavily disturbed by tectonic activity, might leave no fossil record at all. Moreover, intelligence is not always associated with the anatomical markers that make a species recognizable in fossil form. An intelligent species that developed along a fundamentally different morphological path, one that did not require bipedalism or the specific cranial architecture of hominins or fine manipulative limbs, might be invisible to a search built around the physical characteristics of human intelligence. We look for what we know. We have very little basis for knowing what to look for in something genuinely different. Finally, there is the timeline consideration. A species that evolved, achieved technology, and went extinct 50 million years ago would be found, if at all, in Eocene age fossil beds. Those beds exist, and they are actively studied, but they represent a tiny, irregularly distributed sample of the life of that era. A single species, even a dominant one, that survived for only a few million years, a blink by evolutionary standards, might simply never have been encountered in the small fraction of those beds that have been systematically examined. The silence of the fossil record is real. It is evidence of a kind, but it is not proof. There is one domain where the counter-arguments are strongest, and it is a domain Frank and Schmidt considered but could not definitively resolve. It is the question of planetary resource depletion, not just fossil fuels, but metals and minerals. Industrial civilization does not only burn carbon, it mines copper for electrical wiring, rare earth elements for electronics, iron for steel, aluminum from bauxite deposits, lithium for batteries. These materials are extracted from geological deposits, concentrated by smelting and refining, and then dispersed through manufactured products that eventually break down and scatter the metals across the environment. The mining of a major ore deposit leaves a hole in the ground. Over geological time, that hole fills with sediment and the distinctive chemistry of a disturbed ore body, the oxidized minerals at the edge of the excavation, the altered elemental ratios of the surrounding rock can persist for tens of millions of years, recognizable to a trained geochemist as evidence of concentrated removal of material. We have not, as far as systematic geological survey has revealed, found obvious evidence of previously mined ore deposits from deep geological time. If a previous civilization had industrialized on anything like the scale of modern human industry, there should be geochemical anomalies associated with depleted ore bodies in geological sections from the relevant period. The fact that the ore bodies we have found and exploited appear, based on isotopic dating and structural geology, to have been untouched since their formation is meaningful evidence. But, and this is important, ore deposit geochemistry is not routinely surveyed with the question of previous industrial activity in mind. The interpretive framework being applied when geologists examine ore body chemistry is one calibrated to understand natural processes of mineral concentration and depletion, hydrothermal circulation, supergene enrichment, erosion, and secondary concentration. Industrial depletion would produce a different pattern, a clean excavation geometry, characteristic distributions of fine particulates. But this pattern has never been systematically searched for in ancient geological sections, because no one was looking for it. Again, we find what we look for. The Silurian hypothesis invites us to consider what we might find if we looked differently. Step back now from the specific evidentiary arguments and consider the broader context of deep time, because one of the most striking aspects of the Silurian hypothesis is how it changes the way complex life on Earth has to be thought about. Complex multicellular life has existed on this planet for at least 540 million years since the Cambrian explosion. In those 540 million years, the diversity of life has gone through extraordinary transformations. 5 major mass extinction events have each destroyed more than 60% of all species alive at the time, and life has recovered from each one. Between extinction events, evolution has proceeded continuously, producing an astonishing range of body plans, ecologies, behaviors, and cognitive architectures. In that 540 million year span, intelligence has evolved independently multiple times. Vertebrate intelligence, molluscan intelligence in cephalopods, social intelligence in arthropods. Evolution appears to find intelligence reliably when the selective conditions favor it, primarily environments with complex social structures and ecological competition that reward flexible behavior and information processing. The fact that human-level intelligence evolved in our lineage is not evidence that it is extraordinarily unlikely to evolve in general. It is evidence that, given sufficient time and the right conditions, evolution will find this solution. 540 million years is a very long time. It is long enough for intelligence to have evolved, reached technological capability, built a civilization, and gone extinct, not once, not twice, but potentially many times, in species we have never identified, in periods of geological history where the record is too sparse or too altered to tell us who was there. This is not wild speculation. It is an implication of evolutionary biology applied to deep time. The conditions that produced intelligence in the human lineage are not uniquely associated with the Quaternary period. The selective pressures that drive the evolution of complex cognition, social competition, ecological variability, the advantages of behavioral flexibility over instinctual rigidity, existed throughout the Phanerozoic. There is no principled reason why intelligence should have evolved only once. There is every reason to expect it evolved repeatedly. Most such evolutions produced species that achieved complex cognition without crossing the threshold into technology. Intelligence is a spectrum, not a binary. But the possibility that some previous intelligent lineage crossed the threshold, that at some point in the past 500 million years, some species discovered fire, discovered metallurgy, discovered energy extraction from concentrated chemical stores, and built structures and systems complex enough to leave a chemical mark on the planet, cannot be dismissed on biological grounds. It is not biologically implausible. It is, arguably, biologically expected. What is uncertain is whether any such civilization persisted long enough, operated at sufficient scale, and left signatures in geological deposits that have survived long enough to be detectable today. The Cambrian explosion itself is worth dwelling on, because it represents one of the most dramatic and least satisfactorily explained events in evolutionary history, and it sits in interesting relationship to the questions raised by the Silurian hypothesis. Roughly 540 million years ago, the fossil record shows a sudden extraordinary diversification of complex animal life. Before the Cambrian boundary, the Precambrian record contains mostly microbial mats and a handful of enigmatic multicellular organisms known as the Ediacaran fauna, soft-bodied, strange, many of them with no clear relationship to any modern animal group. Then, in a window of geological time estimated at between 10 and 25 million years, virtually every major animal body plan currently represented in the biosphere appears in the fossil record. Eyes, hard shells, complex nervous systems, predator-prey ecological structures, jointed limbs. The full toolkit of complex animal biology shows up in what amounts to an evolutionary instant. The conventional explanation involves a combination of environmental factors, rising oxygen levels in the oceans making aerobic metabolism more efficient, the breakup of the supercontinent Rodinia creating new shallow coastal environments, possible snowball Earth glaciation events clearing the ecological slate, combined with the positive feedback loops of the evolutionary arms races that began once the first complex predators appeared. These explanations are widely accepted and have substantial supporting evidence. But the speed and completeness of the Cambrian explosion has always nagged at evolutionary biologists. The transition from simple Ediacaran body plans to the full diversity of Cambrian fauna is faster than standard evolutionary models comfortably predict, even accounting for the gaps in the Precambrian fossil record. The missing intermediates, the proto-arthropods, the proto-mollusks, the transitional forms that should connect Ediacaran organisms to their Cambrian successors, are largely absent. The Silurian hypothesis does not provide an explanation for this, and it would be overreaching to claim it does. The Cambrian explosion happened 540 million years ago, at a time when the geological record is sparse enough that absence of evidence is entirely expected. But the explosion does serve as a reminder that the history of life on Earth contains evolutionary transitions that we have not fully explained, windows in time where the record shows sudden dramatic change without a complete mechanistic account. That incompleteness is not evidence of anything hidden. It is evidence of the genuine difficulty of reading a record that is hundreds of millions of years old and fragmentarily preserved. But it is a reminder that the history of life on Earth is not a fully solved problem. There are chapters we cannot read clearly, and the honest position is to acknowledge that rather than paper over it with confident assumptions. The late Ordovician extinction is one of the 5 great mass extinctions and deserves careful attention in this context. It occurred approximately 443 to 445 million years ago, at the end of the Ordovician period, and it was catastrophic. Between 70 and 85% of all marine species went extinct in what appears, from the geological record, to have been 2 distinct pulses of extinction separated by approximately 1 million years. The first pulse is associated with a rapid global glaciation event. The supercontinent Gondwana had drifted over the South Pole, and massive glaciers built up over what is now North Africa and South America. Sea levels dropped by up to 100 meters as water was locked in ice. Shallow marine habitats, where most complex Ordovician life lived, were dramatically reduced. Cold, oxygen-depleted waters swept into the oceans as the glacial circulation pattern reorganized. The second pulse, roughly 1 million years later, occurred during a rapid deglaciation. The Icehoit glaciers melted. Sea levels rose. The cold, anoxic, deep waters that had accumulated during the glaciation upwelled onto the continental shelves, poisoning the marine environments that had survived the first extinction pulse. Together, these two events eliminated a remarkable fraction of all complex life on Earth. The recovery took millions of years. Now, from the perspective of the Silurian hypothesis, the late Ordovician is interesting for a specific reason. It represents a window of several million years, ending 443 million years ago, during which complex marine life had achieved considerable sophistication: trilobites, cephalopods, corals, brachiopods, early fish. But the geological record is sparse, and the chemistry of the extinction boundary is not fully resolved. The precise sequence of events at the extinction boundary is debated. The carbon isotope record from this period shows anomalies that have been interpreted in various ways. Could any of the chemical anomalies at the Ordovician extinction boundary reflect the activity of an early intelligent species? No evidence currently supports this reading. The natural glaciation and anoxia mechanisms are well supported by multiple independent lines of geological evidence and are almost certainly correct. But the analytical framework that would be needed to systematically test for industrial signatures in Ordovician age sediments has never been applied, because the question has never been formally asked. The pattern here is consistent, not across one event, not across two events, but across every major geological transition in the history of complex life. The interpretive framework used to study these events assumes natural causes. Natural causes, in almost all cases, are the correct answer. But the Silurian hypothesis reveals that the assumption has never been rigorously tested against the alternative. We have been asking only questions that can produce natural answers, and then citing the natural answers as evidence that only natural questions were worth asking. There is a deeper methodological point embedded in all of this, and it matters beyond the specific question of previous civilizations. It concerns what scientists call the principle of uniformitarianism, the foundational geological assumption that the physical and chemical processes operating today have operated in the same way throughout geological time, and that we can therefore use the present to interpret the past. Uniformitarianism was a revolutionary idea when it was first articulated in the 19th century. Before it, geological catastrophism held that the landscape had been shaped by occasional violent supernatural interventions. Uniformitarianism replaced that framework with a rigorous naturalistic one. Slow, steady, observable processes, erosion, sedimentation, volcanism, tectonics, operating over vast spans of time can account for everything we see. The principle was enormously productive. It is the foundation of modern geology. But uniformitarianism has an implicit assumption buried inside it that is rarely examined. It assumes that the only processes operating on geological timescales are physical and chemical natural processes. It was developed in an era when the concept of a technological species leaving a geological signature was not part of the scientific vocabulary. The possibility that an intelligent species could, through its actions, produce effects equivalent to major geological events, a carbon injection comparable to a volcanic episode, a biodiversity collapse comparable to a bolide impact, was not considered because no such species was known to exist. Now one does. We are it. And the existence of a technological species capable of planetary-scale geological impact changes the interpretive framework that uniformitarianism permits. Technological activity is now a legitimate process to consider alongside volcanism, impacts, orbital forcing, and oceanic circulation changes. For events in the future, everyone accepts this. For events in the present, it is the central concern of climate science. But for events in the deep geological past, events that predate human existence by millions or hundreds of millions of years, it has been effectively excluded from consideration. The Silurian hypothesis is, at its most fundamental level, an argument for expanding the methodological scope of geology and paleontology to include technological activity in the space of possible explanations for geological anomalies, not as the first or most likely explanation, not as a hypothesis to be preferentially favored, but as a hypothesis to be considered, tested, and either ruled out by positive evidence or held open as a genuine possibility. That is not a radical claim. It is a minimal claim, and it has not, historically, been met even at that minimal level. What would it actually take to find convincing evidence of a previous industrial civilization, if such evidence exists anywhere in the accessible geological record? Frank and Schmidt outlined several potential signatures, each with different detection prospects. Carbon isotope anomalies in sedimentary sections from periods of otherwise unexplained rapid climate change represent the most accessible potential signature, because the analytical methods for measuring carbon isotope ratios in ancient sediments are already well developed and widely applied. The challenge is distinguishing between industrial and natural sources of isotopically light carbon, because the two overlap in their chemical fingerprint. More targeted analysis would look not just at the bulk carbon isotope ratio, but at the distribution of specific organic biomarkers, the molecular remnants of particular types of organisms or processes, that might provide higher resolution information about the source of the carbon. Anomalous concentrations of specific heavy metals in thin stratigraphic intervals represent a second potential signature. Industrial smelting of metals produces concentration and dispersal patterns that differ from natural volcanic or hydrothermal metal enrichment. More detailed geochemical profiling of sediment sections from anomalous climate events, including the PETM, the Paleocene-Eocene boundary, various Mesozoic oceanic anoxic events, and the 5 major mass extinction boundaries, looking specifically at the distribution of lead, mercury, cadmium, and other industrial heavy metals, could reveal enrichments inconsistent with natural sources. Anomalous mineral assemblages are a third potential signature. Certain manufacturing processes produce characteristic mineral phases that do not occur naturally, specific glass compositions, synthetic ceramic phases, unusual alloys. These would survive geological time poorly, but in exceptional preservation conditions, perhaps in marine evaporate sequences or in chemically inert deep ocean sediments, traces might persist. A systematic survey of bulk mineralogy in sections from relevant geological periods could potentially identify anomalous mineral phases worth further investigation. None of these searches has been conducted with the Silurian hypothesis as a guiding motivation. All of them are technically feasible with existing analytical methods. The cost would be modest relative to the scientific questions they could help answer. The reason they have not been done is simply that, until recently, no one considered them worth doing, because the question they would address was considered beyond the scope of legitimate geological inquiry. That is changing. Slowly, but it is changing. What would it look like in practice to actually design a search program aimed at testing the Silurian hypothesis systematically? The first requirement is a target list. Which geological periods and which specific geological sections offer the best combination of preservation quality and temporal windows when an industrial civilization would be most plausible? The most favorable windows are ones where complex terrestrial life had existed for long enough to develop large-bodied, cognitively sophisticated vertebrates, which means the Mesozoic and the Cenozoic, the last 250 million years. Of these, the Cenozoic offers the best preserved record, and within the Cenozoic, the Paleogene and Neogene, the last 65 million years, offer increasingly high-quality sediment records as you approach the present. Within that window, the ideal target sections are marine sediment sequences deposited on stable continental shelves in tectonically quiet regions, locations where the sediment has accumulated without major disruption, has not been subducted or deeply buried, and where the time resolution of the record is fine enough to resolve changes on the scale of thousands of years rather than millions. Such sections exist. The deep-sea sediment cores obtained by the International Ocean Discovery Program and its predecessors represent exactly this type of archive. These cores, drilled from ocean basins around the world, provide continuous records of marine chemistry, temperature, and biological change at time resolutions that can, in favorable cases, reach a few hundred years per centimeter of sediment. The analytical program applied to such cores would look for several things simultaneously. First, rapid carbon isotope excursions in sections where no known large-scale volcanic event explains the timing. Second, anomalous enrichments of specific industrial heavy metals, particularly lead, cadmium, and thallium, which have distinctive industrial dispersion patterns in thin stratigraphic intervals that correlate with carbon isotope anomalies. Third, anomalous patterns in the diversity and abundance of marine organisms that suggest rapid ecological disruption inconsistent with the gradual changes typical of orbital forced climate transitions. The key, innovation relative to standard geochemical analysis, is not the methods themselves. All of these measurements are routine, but the framing. Standard geochemical analysis of these sections is designed to reconstruct natural climate variability and identify volcanic or tectonic drivers. An analysis designed to test the Silurian hypothesis would use the same data but apply different interpretive criteria, looking for combinations of signals that together are inconsistent with any known natural process, and that together are consistent with the industrial signature predicted by Frank and Schmidt's modeling. This is not a guaranteed path to a positive result. Most such analyses would almost certainly reveal nothing inconsistent with natural processes, but the existence of the PETM and the other hyperthermals shows that the kind of event this search is looking for, rapid carbon injection with associated ecological disruption, does occur in the geological record. The question is whether any of those events carries a combination of chemical signals that cannot be explained naturally. The search has not been done. It should be. There is a thought experiment worth running, because it clarifies what we should actually expect the geological record of a previous civilization to look like, given everything established so far. Imagine a species that evolved in the shallow coastal environments of the Eocene epoch, roughly 40 to 50 million years ago, in the warm, geologically active margins of what was then the Tethys Sea, in the region that is now the Mediterranean and Middle East. Suppose this species, not resembling any modern primate or indeed any modern mammal, had evolved sophisticated cooperative behavior through a long period of social selection, had developed manual dexterity, and had accumulated cultural knowledge across generations in ways that bootstrap an increasingly complex material culture. Suppose that over a period of perhaps 200,000 years, this species developed metallurgy, starting from the reduction of easily accessible surface copper and tin deposits, and eventually discovered the energy stored in the organic-rich oil shales and coal seams of their coastal environment. Suppose their industrial period lasted 5,000 years. That is a generous estimate, considerably longer than human industrial civilization to date. In that 5,000 years, they burned through easily accessible near-surface hydrocarbon deposits in their region, emit carbon-13 depleted carbon into the atmosphere, warm the planet modestly, acidify the surface oceans in ways that stress carbonate-building organisms, and scatter industrial metals across the sediment record of their habitat. Then, a combination of ecological disruption, resource depletion, or climate destabilization causes their civilization to collapse. The species may continue as a non-industrial population for a few million more years before going extinct in one of the normal background turnover events of evolutionary time. What is left? The 5,000-year industrial period produces a chemical layer in the sediment record of the Tethys Sea region. That layer is now anywhere from 40 to 50 million years old. The Tethys Sea itself closed as Africa collided with Eurasia, a collision that was already underway 50 million years ago, and that continued through the Oligocene and Miocene epochs, eventually producing the Alps, the Zagros Mountains, and the Himalayas. Much of the Tethys seafloor was subducted. What was not subducted was compressed, uplifted, and metamorphosed into the rocks of the alpine Himalayan mountain belt, where it is exposed today in deeply altered form. The chemical layer of the hypothetical industrial civilization's activity, if it was deposited in the deep Tethys, has been recycled into the Earth's interior. If it was deposited on a continental margin that has since been uplifted into the Alps, it may exist in a deformed and metamorphosed state somewhere in the mountain belt. But looking for a chemical anomaly in the marble and schist sequences of an orogenic belt without knowing where to look is an effectively impossible search problem. In shallower shelf environments farther from the collision zone, along what is now the coast of North Africa, or in the sedimentary basins of the Persian Gulf, some Eocene age sediment sequences survive and are accessible. These sequences are actively drilled by the petroleum industry, which routinely produces geochemical logs of their composition. A systematic reanalysis of existing petroleum industry core data from Eocene sections with attention to the specific chemical signatures predicted by the Silurian hypothesis would be feasible with existing data and methods. It has not been done. This is not a claim that such a civilization existed. It is a demonstration that if it had, the evidence for it is not obviously ruled out by what we know, and that the search has not been conducted. The absence of evidence is, here as elsewhere, not evidence of absence. It is evidence of absence of search. The implications of the Silurian hypothesis extend well beyond Earth, and this is perhaps where its deepest significance lies. We are currently engaged in the most ambitious search for intelligent life in human history. Radio telescopes scan the sky for artificial electromagnetic signals. Space telescopes analyze the atmospheric chemistry of distant exoplanets for biological and technological signatures. Probes are sent to Mars, to Europa, to Enceladus, searching for evidence of life. The entire enterprise of astrobiology is built on the assumption that we know what we are looking for, that we can distinguish between natural chemical processes and the products of biology or technology, and that detecting such signals is a matter of sensitivity and patience. The Silurian hypothesis directly challenges this assumption. If we cannot reliably detect the geological signatures of industrial civilization in Earth's own geological record, a record we have been studying for 2 centuries with direct access to the samples, how confident can we be in our ability to detect such signatures at interstellar distances? The atmospheric chemical signatures we look for in exoplanet spectra are largely biological: oxygen, ozone, methane, dimethyl sulfide, compounds whose presence in certain combinations is considered evidence of living chemistry. But technological signatures are different from biological signatures. A civilization in its industrial phase might produce atmospheric anomalies, elevated carbon dioxide, specific industrial pollutants, halocarbons, that overlap in complex ways with natural atmospheric chemistry. A civilization that has passed through its industrial phase, one that has either gone extinct or achieved some kind of sustainable post-industrial state, might leave no atmospheric signature at all. If the history of civilizations typically involves a brief, intense industrial phase, followed either by collapse or by transition to energy sources that leave no atmospheric trace, then the window during which a civilization is detectable by atmospheric chemistry analysis is vanishingly small relative to the potential lifespan of an intelligent species. We might be searching for a signal that most civilizations emit only for a few centuries or millennia, a geological instant, out of histories that span millions of years. This is the Silurian hypothesis applied at interstellar scale. The same problem of temporal window and detectability that makes previous civilizations on Earth potentially invisible to us also makes most civilizations in the galaxy potentially invisible to interstellar search. The absence of detected signals is not strong evidence of absence of civilizations. It is strong evidence that our search methods are calibrated to a very specific and possibly unusual type of signal. The relationship between the Silurian hypothesis and the Fermi paradox deserves careful attention, because the two problems are deeply interconnected. The Fermi paradox is the observation that in a galaxy that is approximately 13.6 billion years old, with hundreds of billions of stars and potentially hundreds of billions of planets, and given that the materials and conditions for life appear to be common, intelligent technological civilizations should have arisen billions of years before us. In all that time, a civilization with even modest expansionist tendencies and technology only slightly more advanced than our own should have been able to colonize the entire galaxy. Yet we detect no evidence of any such civilization. The sky is silent. The galaxy, as far as we can tell, is empty of technological activity, except our own. Various solutions to this paradox have been proposed. The Great Filter hypothesis suggests that somewhere in the chain of development from chemistry to intelligence to technological civilization to interstellar expansion, there is a step so unlikely that it is almost never taken, either behind us, in which case we are extraordinarily rare survivors, or ahead of us, in which case virtually all civilizations fail before reaching interstellar capability. The Zoo hypothesis proposes that advanced civilizations exist, but are deliberately concealing their presence. The Rare Earth hypothesis suggests that the specific conditions that produced Earth are so unlikely to be replicated elsewhere that intelligent life may genuinely be extremely uncommon. The Silurian hypothesis does not directly resolve the Fermi paradox, but it adds a dimension to it that is rarely discussed. The paradox assumes that we are the first technological civilization in the history of Earth, and therefore that Earth represents one data point, a planet that has, apparently, produced one civilization. But if the Silurian hypothesis is taken seriously, if we acknowledge that we cannot rule out previous civilizations on Earth, then Earth might actually represent multiple data points, multiple evolutionary experiments in intelligence and technology, most of which failed to produce long-lasting detectable signatures. Multiple civilizations that rose during the long Phanerozoic interval changed the planet in ways that are now interpreted as natural events and then vanished. If this is the case, it changes the calculation for the Fermi paradox. Rather than asking why a long-lived interstellar civilization has not colonized the galaxy, the question becomes, what is the typical lifespan of a technological civilization before it either goes extinct or transitions to a state that leaves no detectable trace? If the answer is, measured in geological terms, extremely brief, then even a galaxy full of civilizations might produce only rare, fleeting signals, and our failure to detect them would simply reflect the mismatch between our search window and the typical temporal availability of the signals. Earth's own history, if the Silurian hypothesis is correct in its most provocative interpretation, could be a data set for this question. How many times has intelligence arisen on this planet? How many of those instances crossed the threshold into technology? How long did each industrial phase last before collapse or transition? The geological record, properly interrogated with the right questions, might contain information relevant to these questions, compressed into chemical anomalies that have been consistently interpreted as natural events. We are, in this reading, already in possession of data about the typical life cycle of technological civilizations. We are just misclassifying it. But the Fermi paradox intersection goes deeper still. Consider what it would mean for the search for extraterrestrial intelligence if the typical lifespan of an industrial civilization is measured in centuries rather than millions of years. Current SETI strategies are calibrated for civilizations that transmit electromagnetic signals persistently over timescales long enough that, even accounting for the travel time of those signals across interstellar distances, there is a reasonable chance of the signal and our receiving equipment existing simultaneously. A civilization that transmits for 100 years and then goes silent produces a spherical shell of radio waves 100 light-years thick, expanding outward from its origin point. That shell is 0.1% of the diameter of the Milky Way. It passes through any given point in the galaxy for only 100 years, the same 100 years during which our own civilization has been capable of receiving and recognizing it. The probability that this shell intersects Earth during our specific century of radio astronomy is vanishingly small unless civilizations are densely distributed or have been transmitting for much longer than a century. If Earth's own history contains examples of civilizations that rose and fell without leaving easily detectable traces, the implication for SETI is sobering. The galaxy could contain, or have contained, many short-lived technological civilizations without any of them being detectable from the vantage point of Earth in the 21st century. The silence of the cosmos may not be the silence of emptiness. It may be the silence of geological time applied to civilizations, the silence of things that ended before their signals could reach us, or during windows of time so narrow that the probability of any given civilization receiving them is small. This reframing does not make the search for extraterrestrial intelligence less important. If anything, it makes it more urgent. It suggests that the window during which any given civilization is detectable may be narrow, which means that any signal we are lucky enough to receive carries extraordinary information, not just about the civilization that sent it, but about the possibility of surviving the industrial bottleneck that seems to define the most dangerous phase of technological development. A civilization that is still transmitting after thousands of years has, by that fact alone, demonstrated that survival is possible. That may be the most important message any signal from space could carry. There is another dimension of the exoplanet search that the Silurian hypothesis speaks to directly, and it concerns what we think we would see if we found a world that had previously hosted an industrial civilization and no longer did. The James Webb Space Telescope is capable of analyzing the atmospheric chemistry of planets orbiting nearby stars by observing the slight reduction in starlight as the planet transits its host star. Different molecules absorb different wavelengths of light, and by comparing the spectrum of the star with and without the planet's atmosphere in front of it, the composition of that atmosphere can be inferred. This technique has already produced remarkable results. The detection of water vapor, carbon, dioxide, methane, and other molecules in exoplanet atmospheres is now routine. The biosignatures that exoplanet astronomers search for most eagerly are the ones that indicate active biological processes: oxygen, maintained at atmospheric concentrations that require continuous biological production because it reacts rapidly with surface rocks in the absence of life. Methane coexisting with oxygen, a combination that is chemically unstable and requires constant replenishment. Dimethyl sulfide, produced exclusively by certain marine organisms. These are the signatures of a living world, a world where biology is actively altering the atmospheric chemistry. A world that previously hosted a technological civilization, but no longer does, might have a very different atmospheric signature, and that signature has never been systematically characterized. If an industrial civilization burned fossil fuels and then went extinct, leaving the planet to recover naturally, the atmospheric carbon dioxide would gradually be drawn down by geological processes over millions of years. The oxygen might recover, the methane might stabilize, the unusual isotopic signatures might be erased by photochemical and depositional processes. After tens of millions of years, the atmosphere might look essentially natural, a world in a post-civilization recovery state that is chemically indistinguishable from a world that never hosted technology at all. If the recovery period is long compared to the industrial period, and for our own planet, the recovery from the current carbon pulse is estimated to require hundreds of thousands of years, then the window during which an exoplanet's atmosphere shows clear technological signatures is extremely narrow relative to the full habitable lifetime of the planet. We could look at hundreds of habitable worlds and find no unambiguous technological signatures, not because none of them ever hosted civilizations, but because none of them is currently in its industrial phase, and the chemical evidence from previous industrial phases has been erased. This is the Silurian hypothesis applied to exoplanet astronomy, and it suggests that our search for technosignatures in exoplanet atmospheres, even if conducted with perfect sensitivity and comprehensive coverage, might systematically fail to detect civilizations that have already passed through their technological phase. The absence of detected technosignatures in this framework is not evidence that the galaxy is empty. It is evidence that civilizations, if they exist, are brief. There is one further dimension of the deep time problem that has not been sufficiently addressed, and it concerns what happens not just to physical and chemical evidence, but to the biological evidence of intelligent species themselves. We know the history of human intelligence in considerable detail. Homo sapiens appears in the fossil record roughly 300,000 years ago in Africa. Before that, a succession of ancestral species extends back through Homo heidelbergensis, Homo erectus, Homo habilis, and the earlier Australopithecines to the common ancestor we share with chimpanzees roughly 6 to 7 million years ago. The brain sizes of these ancestral species track broadly with the complexity of their tool cultures and the progression from the earliest stone flakes to the sophisticated composite tools of the Upper Paleolithic parallels, a gradual increase in cranial volume and the complexity of archaeological sites. This is an unusually well-preserved record. It is well-preserved for specific reasons. The East African Rift System, where much of early hominin evolution took place, is geologically active in ways that produce fine-grained sedimentary deposits ideal for fossil preservation. The shallow lake beds of the Rift Valley accumulated sediment rapidly, burying bones quickly enough to prevent decomposition. The subsequent uplift of these deposits has exposed fossil-bearing strata in accessible outcrops. The combination of these factors, rapid burial, stable depositional environment, subsequent exposure, produced a fossil record of human evolution that is exceptional relative to the typical quality of the Cenozoic record for any other lineage. Now ask, what are the chances that a species evolving intelligence in a different part of the world during a different geological period, in a different depositional environment, would leave a comparably detailed fossil record? The honest answer is very low. The conditions that preserved the Australopithecines are not typical conditions. Most species evolving in most places during most geological periods leave no fossil record at all. A species that evolved intelligence in a coastal environment, where erosion is vigorous and preservation is poor, would be invisible to future paleontologists even if it had thrived for millions of years. This is not a minor consideration. It fundamentally changes what the silence of the fossil record means. The fossil record is not an unbiased survey of which species have existed on Earth. It is a biased sample weighted toward organisms that happened to live in environments with unusually favorable preservation conditions. The absence of a fossil record for an ancient intelligent species tells us only that such a species did not live in the kind of environments that tend to produce fossils. It tells us nothing definitive about whether such a species existed. And there is a deeper point. The anatomical features that make a species recognizable as intelligent, the relative expansion of the cerebral cortex, the reorganization of the prefrontal areas, the modification of the vocal tract and hand morphology, are features of soft tissue that do not directly fossilize. We infer intelligence from skull shape and brain endocast morphology, and from the association of skeletal remains with manufactured objects. But the correlation between skull shape and intelligence is imperfect even within our own genus, and there is no principled basis for assuming that only one type of skull shape can house an intelligence capable of technological civilization. A species with a fundamentally different body plan, with nervous tissue distributed differently, with manipulation accomplished through different anatomical structures, with social and cognitive organization built on a different evolved substrate, might achieve technological capability and leave no recognizable trace in the skull morphology record even if it did fossilize. We are looking for human-shaped intelligence in the fossil record because human-shaped intelligence is the only kind we know. That is an extraordinary extrapolation from a sample size of 1. The specific name chosen for this hypothesis, Silurian, carries a resonance worth pausing over. Adam Frank and Gavin Schmidt borrowed the name from a fictional species in the British science fiction series Doctor Who, the Silurians, an ancient race of intelligent reptiles who supposedly built an advanced civilization during Earth's deep prehistory, went into hibernation to survive a predicted asteroid impact, and awoke in the modern era to find their world claimed by a newer species. The fictional Silurians are a metaphor for the anxiety the hypothesis addresses, the discomfort of discovering that you are not the first, that the world you call yours has been home to something before you, that your claim to originality and uniqueness is weaker than you believed. In the television narrative, the encounter between humans and Silurians is tragic, a confrontation between two species, each convinced of its own primacy, each unwilling to share a world that can only, in the dramatic logic of the story, belong to one of them. The metaphor is revealing precisely because the scientific hypothesis is nothing like its fictional inspiration. The Silurian hypothesis does not suggest that a previous civilization is waiting to reclaim the planet. It suggests that civilizations may be far more temporary than we instinctively assume, that the marks a civilization leaves on the world are smaller and more fragile than its inhabitants, while they exist, can possibly believe. Every civilization is, from the perspective of geological time, a brief flicker, a few centuries of fire, a thin layer in the rock, a chemical whisper that the planet absorbs and continues. What the fictional Silurians have that the real hypothesis lacks is persistence. They survived. They remembered. They had grievances. The geological record does not contain grievances. It contains chemistry. It does not preserve civilizations. It preserves the faint thermodynamic consequences of civilizations, the waste heat, the altered isotope ratios, the trace metals scattered by industry, until those consequences too are absorbed and erased. The real Silurian hypothesis is more unsettling than the fiction, in a particular way. The fiction is unsettling because another species still exists to challenge our primacy. The hypothesis is unsettling because nothing remains. Whatever came before, if anything came before, is truly gone. Not hiding, not dormant, erased. The planet has moved on, indifferent to the question of who was here. Look down at the ground beneath your feet. Wherever you are standing, on city pavement, in a field, at the edge of a coastline, you are standing on top of a column of rock that extends downward through meters, through hundreds of meters, through kilometers, into a geological record that stretches back billions of years. Every layer in that column is a moment in time. Every chemical composition, every fossil fragment, every trace element distribution is a record of something that happened. Most of what that record contains, we can read. We have spent 2 centuries developing the tools and frameworks to extract information from rock. And those tools are sophisticated, those frameworks are rigorous, and the story they tell about the history of this planet is one of the great achievements of human scientific inquiry. But the tools were built with certain questions in mind, and not others. The frameworks were constructed around certain assumptions about what kinds of events are worth looking for. The story they tell is the story of natural processes, volcanism and erosion, extinction and recovery, ice ages and warm periods, mass extinctions and evolutionary radiations. It is a story of unimaginable grandeur and complexity. And it is almost certainly largely true. What the Silurian hypothesis asks is whether, hidden within that true story, there might be chapters that do not fit neatly into the natural process framework, whether some of the anomalies that have been attributed to volcanism or methane hydrates or orbital forcing might carry, beneath or within or mixed with those natural signals, the faint residue of something else, something brief, something local, something that thought and built and burned and was gone before the rock closed over it. We cannot currently answer that question. That is the honest position. Not because the question is unanswerable in principle, but because the search has not been conducted. The hypothesis has not been tested at the level of rigor and systematic inquiry it deserves. The geological record has not been examined with this question as a guiding motivation. That absence of search is itself a data point. It tells us something about the assumptions embedded in science, that the question of previous civilizations was so far outside the considered space of possibilities that it required 2 scientists with the intellectual courage and disciplinary independence to formalize it before anyone thought to ask it systematically. It tells us that scientific communities, like all communities, have blind spots shaped by shared assumptions, and that the most important questions are sometimes the ones that no one has thought to ask. The Silurian hypothesis is, in this sense, a gift, not because it provides answers, because it clarifies precisely which answers are still open. Consider one more implication, perhaps the most significant, and it is not about the past, but about the future. The Silurian hypothesis was developed in the context of concern about modern climate change. Frank and Schmidt were, in part, motivated by the question of what geological signature our own industrial civilization will leave. What future scientists, or future intelligent life, would see in the rock record of our era, and how they would interpret it. The paper is, in a sense, a thought experiment about our own legacy viewed through the lens of geological time. That thought experiment is uncomfortable in a way that has nothing to do with previous civilizations. It is uncomfortable because it forces a confrontation with scale. The chemical signature of our civilization, the carbon isotope excursion, the radioactive isotopes, the synthetic compounds, the biodiversity collapse, will be legible in the geological record for somewhere between tens of millions and hundreds of millions of years. The civilization producing that signature has existed for roughly 300 years. The ratio is approximately 1 to 10,000. For every year of industrial activity, 100,000 years of geological legibility. We are 300 years into a process that will mark the planet for geological epochs. The decisions made in the next 100 years will determine how large that mark is, how deep the carbon spike goes, how complete the biodiversity collapse is, how long the recovery takes. Whether the PETM is the best geological analog for what we are doing, or whether what we are doing is the beginning of something the geological record has not seen, since an event far more catastrophic, depends on choices that are being made in the current century. Previous civilizations, if they existed, faced a version of this same reckoning. A species that discovers how to extract and burn concentrated energy is a species that has crossed a threshold, with no easy return. The concentrated energy enables growth, enables complexity, enables the kind of compounding capability that builds civilizations. But the chemical consequences of that burning accumulate in the atmosphere and the ocean at a rate that the biological and geological systems of the planet did not evolve to absorb quickly. The civilization that reaches industrial capability faces, almost inevitably, a moment when the consequences of its own power must be reckoned with. If previous civilizations existed on Earth, and their signals are among the geological anomalies we are still trying to explain, then they faced that reckoning and did not survive it, or survived it by transitioning to something so different that they left no further detectable trace. The geological record doesn't tell us which. It doesn't tell us whether the transition was catastrophic or successful, whether the civilization ended in extinction or in a kind of post-industrial equilibrium we would not recognize as civilization by our current standards. It tells us only that the industrial signal, if it is there, is thin and isolated, that it did not persist indefinitely, that the period it represents was brief. This is not a comfortable message, but it is an honest one. The fossil record contains a truth that human civilization has been slow to absorb. It is the truth of impermanence at scale, not impermanence in the human sense of individual mortality. That is familiar and has been philosophically accommodated across every culture. This is impermanence at the civilizational scale. The scale at which great experiment after great experiment in complexity and coordination and intelligence runs for what feels, from inside it, like forever, and then ends. And the rock absorbs it. And the world continues. The dinosaurs are the most famous example, but they are actually not the most instructive one for the present question. The dinosaurs were not erased by anything internal to their civilization. They had no civilization. They were eliminated by an external event so vast and violent that it deposited a global layer of iridium visible in every stratigraphic section from every continent. Their extinction was not a failure of judgment. It was an asteroid. The mass extinctions driven by climate change, the end Permian, 252 million years ago, the largest extinction in the history of complex life, in which perhaps 90% of all species died, are more instructive. They were driven by internal Earth processes, massive volcanism in the Siberian traps releasing carbon dioxide and toxic gases over hundreds of thousands of years, warming the planet, acidifying the oceans, deoxygenating the deep waters, until the atmospheric and oceanic chemistry had shifted so far from the conditions in which the existing biosphere had evolved that most of what lived simply could not survive. The Permian extinction was caused by the planet doing to itself, through volcanic processes, what industrial civilization does through burning. The lesson in the rock is not that extinction is inevitable. It is that planetary chemistry is connected, that small changes in the composition of the atmosphere and ocean propagate through the biosphere in ways that are not immediately obvious from inside the system producing the changes, and that the timescale of planetary chemistry response is shorter than it appears when measured against geological deep time. The PETM took 20,000 years to onset and 200,000 years to recover. Those numbers seem slow to a human. To a civilization, to any civilization that has not yet crossed the threshold of understanding its own planetary impact, they are fast enough to be catastrophic. Consider what we are doing to ourselves from the perspective of a geologist 50 million years in the future. This future scientist, using instruments we cannot imagine, pulls a core sample from the compressed remains of what is now the North Sea Basin. The core passes through hundreds of meters of ordinary Miocene and Pliocene sediment, then through a thin but distinctive layer that stands out chemically from everything above and below it. The carbon isotope ratio shifts sharply negative at the base of the layer. Heavy metal concentrations spike: lead, cadmium, mercury, arsenic. The abundance of pollen from agricultural species dominates the palynological record within the layer, replacing the mixed natural forest assemblages of the preceding sediments. The abundance and diversity of marine organisms drops sharply and then partially recovers. Near the top of the layer, certain long-chain organic molecules, partially degraded but still structurally identifiable, suggest the former presence of complex synthetic polymers. And then, above the layer, ordinary sedimentation resumes. The layer is perhaps 3 centimeters thick. What does this future scientist conclude? Within the natural process interpretive framework, the most obvious explanation is a combination of minor volcanism and an unusual climate event. Perhaps a brief warming episode driven by orbital forcing, associated with some methane hydrate destabilization that temporarily stressed the marine ecosystem. The heavy metal spike might be attributed to hydrothermal activity. The polymer-like molecules are ambiguous, possibly degraded natural organic compounds. The future scientist writes up the core analysis and moves on. The 3-centimeter layer joins the catalog of mid-quaternary geochemical anomalies, dutifully recorded and awaiting further study. This scenario is not fanciful. It is, modulo some details about the specific chemistry of preservation and the specific analytical capabilities of future science, a reasonable projection of what will happen to our evidence. Not because future scientists will be less capable than us, because the geological record is genuinely ambiguous and because the interpretive frameworks applied to it are calibrated to natural processes. What could change this outcome? Only one thing: the idea that technological civilizations are a possibility worth testing for. If the Silurian hypothesis, or its intellectual descendants, becomes part of the standard toolkit of geological interpretation. If future scientists learn, as a matter of basic training, to test anomalous chemical layers for technological signatures alongside volcanic and orbital and hydrothermal signatures, then our 3-centimeter layer will be examined with the right questions. The combination of signals will be recognized as consistent with industrial activity. And instead of being cataloged as another mid-quaternary anomaly, our era will be recognized for what it is. We are, in this sense, the first civilization in the history of Earth to have the conceptual tools necessary to leave ourselves a recognizable mark in the geological record. Not because the physical chemistry is any different. Because we can now define what the mark of a civilization looks like and tell future observers what to look for. Frank and Schmidt's paper is, among other things, a message in a bottle. It defines the signature of technological civilizations in terms that any sufficiently advanced geological science can test. If it propagates forward, if it becomes part of the interpretive framework of future geological science, then it closes the loop that the Silurian hypothesis opened. Future scientists will know what to look for. And whether or not they find evidence of previous civilizations, they will at least be asking the right question. That is, perhaps, the most practically important contribution of the Silurian hypothesis. Not its implications for the past, but its implications for the future of scientific methodology. A science that does not know what questions to ask cannot recognize the answers even when they are preserved in the rock. A science that does know, that has explicitly defined the signature of technological activity and built that definition into its interpretive framework, has a chance. The question is whether our civilization will last long enough to ensure that this knowledge is passed on. Whether the paper published in 2018 will be read in 2018 and in 2028, and by whatever scientific tradition exists when the cores that record our era are finally pulled. Whether the chain of understanding holds across the civilizational transitions that lie between now and then. That is a question the rock cannot answer. It is a question only we can answer, by what we do in the time we have. One more aspect of this problem deserves to be named because it carries weight that extends beyond science into something closer to the fundamental question of what it means to be a conscious species on a geological planet. The Silurian hypothesis forces a confrontation with what might be called the loneliness asymmetry. We feel alone in the universe because we have found no unambiguous evidence of other intelligent life, not elsewhere in the cosmos, and apparently not in the history of our own world. That loneliness shapes how we think about our significance. If we are the only technological species this planet has ever produced, then the emergence of human civilization was a singular event in 4.5 billion years of Earth history, a vanishingly unlikely accident that we instinctively elevate into evidence of our uniqueness and importance. The loneliness becomes, in some interpretations, a kind of privilege. But the Silurian hypothesis complicates this. If the geological record cannot rule out previous civilizations, if the very tools we would need to detect them are too coarse to separate their signatures from the noise of natural geological processes, then our apparent uniqueness may not reflect an actual uniqueness. It may reflect a detection failure, the loneliness we feel when we contemplate our place in deep time may be, at least in part, an artifact of the limits of our ability to read the past. This does not mean we are not alone. It means we do not know whether we are alone. And there is a profound difference between those two states. The first is a fact about the world. The second is a fact about the limits of our knowledge. Living with genuine uncertainty is harder than living with confident loneliness, because it removes the consolation of definiteness. It replaces the clean narrative. We are the first, we are singular, our civilization is the one story this planet has ever told, with something more ambiguous and more demanding. More demanding because it asks, if something was here before, what did they discover? What did they fail to see that cost them everything? What did the planet look like to the last generation of a civilization that had burned through its resources and watched its climate destabilize? Did they understand what was happening? Did they have, in whatever cognitive form their intelligence took, the equivalent of science, the ability to measure, to model, to predict, to recognize in the chemistry of their atmosphere the signature of their own undoing? Or did they lack that capacity? Did the specific cognitive architecture of their intelligence, shaped by evolution for fitness in their particular ecological context, not for abstract reasoning about planetary-scale chemistry, simply not extend to understanding systems as large and interconnected as the climate? Did they do what many species do when faced with conditions that exceed the bounds of their evolved behavior? Continue doing what had worked before until the conditions had changed too far? The geological record cannot answer these questions. The compressed chemical layer cannot tell us what the inhabitants of the civilization it records thought, felt, understood, or chose. It records only the thermodynamic consequences of their activity, not the narrative of their inner experience. But we can ask these questions about ourselves. Because we are here, because we are the civilization that currently sits inside the same reckoning that any previous civilization would have faced. Because the choice between understanding planetary-scale consequences and failing to understand them is not a historical question. It is the defining question of the present century. The Silurian hypothesis is, in this reading, not fundamentally a question about the past. It is a mirror held up to the present. It asks, what kind of geological layer do we want to leave? One that is recognized by whoever comes after as the brief, intense pulse of a civilization that burned and collapsed? Or one that tells a different story, the story of a species that understood what it was doing to its planet and changed? Only one of those outcomes produces a civilization that is still here to read its own geological record. Only one of those outcomes means the question of whether we were the first will eventually be answered, rather than permanently closed. The question that opened this journey has no definitive answer. Were we preceded? Did something else stand on this world before us, look up at the same stars, alter the same atmosphere, burn through some version of the same concentrated energy, and then become a thin layer in the rock? The honest answer is, we do not know. Not confidently. The geological record, as presently interrogated, cannot rule it out. The interpretive frameworks applied to that record were not designed to test for it. The searches that would be needed to either confirm it or provide meaningful constraints have not been conducted. The question has been outside the domain of scientific consideration for so long that the absence of evidence has been mistaken for evidence of absence. The philosopher Karl Popper defined science in terms of falsifiability. A claim is scientific if it is possible, in principle, to gather evidence that would show it to be false. The Silurian hypothesis meets this standard. It is falsifiable. Not easily, not cheaply, not in a single experiment, but in principle, a sufficiently comprehensive geochemical survey of well-preserved geological sections from the appropriate time windows could either find anomalous signatures consistent with industrial activity and inconsistent with known natural processes, or find nothing of the sort and thereby set meaningful limits on how large or how widespread any previous civilization could have been. The search can be designed. The methodology can be defined. The questions can be made precise enough to test. What has been lacking is not the intellectual tools or the analytical capability. What has been lacking is the recognition that the question is worth asking. That recognition now exists. The paper has been published. The framework has been defined. The conversation has begun. Science does not always move quickly when it confronts a question that challenges the deepest assumptions of a field. Continental drift was proposed in 1912 and remained controversial for 50 years before the accumulation of ocean floor evidence made it undeniable. The impact hypothesis for mass extinctions was proposed in 1980 and faced significant resistance before becoming consensus. The pattern is consistent. Questions that require revision of foundational assumptions take time, not because the evidence is unavailable, but because the question must first be recognized as legitimate before anyone will invest in gathering the evidence to answer it. The Silurian hypothesis has now been recognized as legitimate, at least within the subfield of astrobiology, and among a growing number of geochemists and paleontologists who have engaged with Frank and Schmidt's framework. What remains is the investment, the systematic surveys, the targeted analyses, the re-examination of existing core archives with new interpretive tools that would begin to answer the question in any rigorous sense. That investment may come in the next decade. It may come in the next century. Or it may wait until some other piece of anomalous evidence, a chemical signature that simply cannot be explained by any natural process, discovered in a context that forces the question into the foreground, makes it unavoidable. Until then, the uncertainty stands. And the uncertainty is the point. That uncertainty is not a failure of science. It is science working exactly as it should, identifying the precise limits of what can be known, naming the assumptions embedded in existing frameworks, and opening the question space to include possibilities that were previously excluded without examination. The discomfort of not knowing is the appropriate response to a genuine epistemic situation. Comfortable certainty in the face of unexamined assumptions is not knowledge. It is the appearance of knowledge, maintained by the refusal to ask the question that would disturb it. The Silurian hypothesis disturbs the question. It does not provide comfort. It provides clarity. Clarity about what is and is not established, what has and has not been looked for, what can and cannot be known given the current state of investigation. That kind of clarity is more valuable than false certainty, even when it is harder to live with. The geological record extends beneath every patch of ground on this planet. It is billions of years deep and contains within it the compressed, transformed, partially erased history of everything that has ever occurred on the surface of this world. Most of that history will never be read. The planet has destroyed too much, transformed too much, erased too much. But some of it remains. Some of it is accessible. Some of it has not yet been examined with the right questions. Somewhere in that record, in layers that are currently classified as volcanic anomalies, or methane hydrate release events, or orbital forced climate perturbations, there may be something else. Or there may not be. The planet is not withholding the answer out of indifference. The planet does not have an answer to withhold. It has chemistry. What we make of that chemistry depends on the questions we bring to it. What we do know is this: 4.5 billion years. Complex life for 540 million of those years. 50 major extinction events in that span. Intelligence that has evolved independently multiple times in the animal kingdom. A geological record that has destroyed the vast majority of what was ever deposited at the surface of this planet. A chemical signature overlap between industrial activity and natural geological events that makes the two effectively indistinguishable at the resolutions available in deep time. Against that background, the confident assertion that we were first, that in all of Earth's long history, across all of the Phanerozoic, the thread of technological intelligence is entirely singular and recent, is not a conclusion supported by evidence. It is an assumption built into the questions we have chosen to ask. That assumption may be correct. The balance of available evidence, interpreted honestly, does not strongly favor previous civilizations. Frank and Schmidt's assessment, That such civilizations are unlikely but cannot be ruled out is the appropriate scientific position. The fossil fuel argument has genuine force. The fossil record's silence, while ambiguous, is real. The absence of undeniable artifacts, while explained by preservation mechanics, is conspicuous. But the appropriate scientific position is not the same as certainty, and the appropriate response to genuine uncertainty is not to maintain the default assumption indefinitely. It is to design the searches that would test it. There is something quietly extraordinary about living at the moment when this question is being formally raised for the first time. It would be natural to expect that fundamental questions about the history of intelligence on Earth would have been exhaustively examined by now, that after 2 centuries of geology and paleontology and geochemistry, the question of whether any previous civilization left traces in the geological record would have been clearly settled. The fact that it has not been examined seriously until 2018 is not a failure of science. It is a reflection of how much is genuinely unknown. Science proceeds by expanding the space of questions it considers worth asking. Every expansion is, at the moment it happens, surprising, because the questions that have been excluded always seemed either obvious or absurd, and their inclusion seems like it should have happened long before. Continental drift was considered absurd before it was considered obvious. The asteroid impact origin of mass extinctions was laughed out of scientific meetings before it became consensus. The idea that the human species is causing a mass extinction event comparable to those of deep geological time was considered alarmist before it became a central preoccupation of ecology and earth science. The Silurian hypothesis follows this pattern. The question it poses will seem, to a future generation of scientists, like one that should have been asked decades or centuries earlier. Why did it take until 2018 for anyone to formally examine whether the geological record could contain evidence of previous technological activity? Probably for the same reason all delayed expansions of the question space happen. Because the assumption they challenge was so deeply embedded in the shared background of the field that it was never identified as an assumption. It was identified as a fact. The fact was, we were first. The new question is, how confident can we actually be of that? There is something quietly extraordinary about living at the moment when this question is being formally raised for the first time. It would be natural to expect that fundamental questions about the history of intelligence on Earth would have been exhaustively examined by now, that after 2 centuries of geology and paleontology and geochemistry, the question of whether any previous civilization left traces in the geological record would have been clearly settled. The fact that it has not been examined seriously until 2018 is not a failure of science. It is a reflection of how much is genuinely unknown. Science proceeds by expanding the space of questions it considers worth asking. Every expansion is, at the moment it happens, surprising, because the questions that have been excluded always seemed either obvious or absurd, and their inclusion seems like it should have happened long before. Continental drift was considered absurd before it was considered obvious. The asteroid impact origin of mass extinctions was laughed out of scientific meetings before it became consensus. The idea that the human species is causing a mass extinction event comparable to those of deep geological time was considered alarmist before it became a central preoccupation of ecology and earth science. The Silurian hypothesis follows this pattern. The question it poses will seem, to a future generation of scientists, like one that should have been asked decades or centuries earlier. Why did it take until 2018 for anyone to formally examine whether the geological record could contain evidence of previous technological activity? Probably for the same reason all delayed expansions of the question space happen. because the assumption they challenge was so deeply embedded in the shared background of the field that it was never identified as an assumption. It was identified as a fact. The fact was, we were first. The new question is, how confident can we actually be of that? Think about what it means to hold this uncertainty honestly. Science is very good at producing confident answers to well-defined questions. It is less practiced at sitting with questions that are, for the moment, genuinely unresolvable. Questions where the honest answer is not a probability estimate or a confidence interval, but a clear-eyed acknowledgement that the evidence available is insufficient to decide. The Silurian hypothesis is one of those questions, and it matters that it is held honestly because the alternatives are worse. The alternative on one side is confident denial, asserting that no previous civilization existed on the grounds that we have found no obvious evidence of one, without accounting for the preservation mechanics that would have destroyed that evidence. This is false certainty. It is the kind of certainty that has been wrong repeatedly in the history of science, and it is wrong here for reasons that are now clearly articulated. The alternative on the other side is credulous inflation, treating the absence of proof as proof of presence, reading ancient geological anomalies as deliberate alien artifacts, populating the past with civilizations for which there is no positive evidence. This is the mirror image error, and it has its own tradition in popular culture and fringe science, where every unexplained geological feature becomes evidence of a lost technologically advanced people. That tradition takes the Silurian hypothesis and inflates it into something its authors specifically disclaimed. It is not honest engagement with uncertainty. It is the substitution of a preferred narrative for the uncertainty itself. The honest position is the one Frank and Schmidt articulated. We cannot rule this out, we very much doubt it, and the question deserves rigorous testing. That is the position of mature science confronting its own limits. It is uncomfortable because it does not resolve the story. It leaves the question open. And open questions are harder to live with than closed ones, even when closure is false. But they are more truthful. And in the long run, truth is the only foundation on which any understanding of this planet, its past, its present, and whatever future it offers, can be built. Stand on the edge of a cliff face where the geological strata are exposed, one of those places where the rock has been cut by a river or a road or tectonic forces, revealing the layers in cross-section. Each line in the rock is a period of time. The bright band of limestone is an ancient seafloor. The dark carbonaceous layer is a buried swamp. The thin red seam of oxidized minerals is a period of exposure and weathering. Time made visible, readable in stone. Somewhere in a cliff face like this, somewhere in the world, if a previous civilization ever existed, there is a layer thinner than your finger, perhaps compressed to the width of a pencil line. A layer that contains, in the proportions of its elements, the residue of something that thought, that planned, that built, that watched fire and understood it and decided to make more. That layer may be inaccessible. It may have been subducted, metamorphosed, erased. It may be sitting, unrecognized, in a core sample in a petroleum industry archive, labeled as a minor geochemical anomaly attributed to natural processes, never reanalyzed with the right questions. It may not exist at all, may have never been deposited, because nothing ever crossed the threshold that we are still learning to navigate. The planet does not tell us which of these is true. It keeps its own timeline, indifferent to our need for narrative, our hunger for the comfort of knowing where we stand in the long story of this world. It records what happens, and then, given sufficient time, erases the record. It is not a museum. It is not an archive. It is a living geological process that transforms and recycles and continues. What remains for us is the question. And the question is not a small one. It sits at the intersection of every concern that defines this moment in the life of a technological species. The fragility of the systems we depend on, the brevity of the window we have to act, the humility required to recognize that we are not the first species to believe that it would last forever, and the responsibility that comes with being, as far as we presently know, the only intelligence alive on this planet that can read the record, understand the chemistry, grasp the stakes, and choose differently. Whether or not something came before, something is here now, and the rock is still recording.